So we are project 8. So we are working on JWST galactic spectral SEDs, and we are trying to fitting them using Beagle. So to be even more clear, so this is an example of galactic spectra. So it's one from Beagle, and it's z equals 0. So that's why you have a part of it which is in UV and the other part which is in visible. Some interesting things on that. First is that the break is not at the Lyman break, but at the Lyman alpha. But this other break is on the break. And you have also a few interesting lines, H beta, O3, and H alpha. So those are the interesting lines because those are intense. And so in our case, we are trying to see some galaxies which are redshift. And so this is why you have the redshift on the y-axis. And you can see that those lines are going to the infrared, and you have above the filters from JWST. So you can see why we are using JWST just because of the redshift. And you have all the stuff I mentioned, which are highlights. And to be slightly more precise, it's not like random JWST data. We are looking at JADES. So it's one of the largest surveys from JWST. It's almost 1,000 hours of photometry and spectroscopy. And we also use a part of CONDELS, which is HST data.
Yeah, and so kind of just briefly about the SED fitting procedure we took. So we first curated a sample, collected the HST and JWST photometry that is a part of JADES, and that is something that we input into Beagle along with inputs of the star formation history, nebular gas, and dust, which we use relatively uninformative priors for. This all goes into Beagle, which is a Bayesian analysis SED fitting code. And what we're able to output is the same input parameters, but with statistical constraints. And we're able to get mock spectral templates that were fit to the photometry data after it was convolved. So to be a little more specific about the selection that we used, we were trying to select for extreme O3 H beta emitters. And so in particular, we were looking at things with H beta O3 equivalent widths greater than 200 angstroms. And so we used 4 JADES filters to make our selection. And this gave us 30 galaxies in 2 redshift bins, where in our lower redshift bin, we had an average or a median O3 H beta equivalent width of about 300 angstroms, and in the higher redshift bin, 16 galaxies with a median equivalent width of 470 angstroms. So you'll note that our higher Z bin has on average higher equivalent width in these lines. And so these are kind of just a few examples in each at each redshift range of some of the fits that we got out. And overall, we find that there's a larger variety in the fits that Beagle gets in our lower redshift bins. So you'll see that across the whole sample, there's some potential Balmer jumps in the most extreme O3 H beta emitters. And in our lower redshift bin, we get a variety of things like Balmer breaks and dusty galaxies. So yeah.
Hi, everyone. Okay, so I'll just talk you a little bit about how to use results from Beagle to infer the properties of the galaxies in our sample. First of all, as Zoraida has just said, we are selecting the most extreme galaxies in our catalog. So one may wonder, are they all AGN? That's why we took the masses and the emission lines from Beagle to build a mass excitation diagram. And as you can see, our data, so the yellow hexagon in these plots, lie all below the demarcation line between AGN and star-forming galaxies. In addition, their equivalent width are consistent with the trend observed in other extreme star-forming galaxies at high redshift. So we are considering starburst galaxies with extreme conditions. And such conditions reflect in highly ionized systems. In the plot on the left, yes, we reported how the gas phase metallicity from Beagle varies with the ionization parameter. So as you can see, our samples exhibit on average a low metallicity and very high ionization parameter. And just as a reminder, the ionization parameter tells you the number of photons ionizing hydrogen per hydrogen atom. So these are really ionized systems, but are also very efficient ionizers as parameterized by psi ion. So in the plot on the left, you can see that all our sample is offset from the average value of psi ion. And this means that these extreme free emitters are indeed a great laboratory for studying, for example, reionization or more in general, Lyman continuum emitting escape.
Okay, we'll be discussing the mass metallicity relation. This is the nebular metallicity in relation to the stellar mass, and we can also see the error bars. And also we compared our samples with other study previously, not sorry for not mentioning in the reference here, but this is someone else's work from previous study with similar redshift with our sample. And here is, we can see from this small circle that our metallicity is in line with this previous study. And this is the gas phase metallicity in relation to stellar mass.
Okay, we focused on around the redshift is 3 or 6, but we also have some result for the redshift 8.3. This, I show the data from HST and the JWST data, but actually this galaxy is observed by ALMA, but the Beagle cannot use it, so we didn't use ALMA data actually. Yeah, this is a really high redshift, so the 500 mega year baby galaxy, and it's composed of 3 big clumps. Yes, here I show the SED or best fitting. So yeah, in general, we can see strong emission. So we can consider or interpret that this galaxy have a high star formation rate and highly ionized. And we can also see the strong fully bound continuum emission. So it shows we can interpret there is a hot stars and emit enough ionizing photons. And my last slide is this. By using Beagle, we can know a lot of physical parameters. For example, there's a stellar mass. Yeah, we can see it's small mass, but actually we didn't use ALMA data, so maybe it can be underestimated. And it also shows a star formation rate, optical depth, and the ionized parameter. And yeah, the result, this shows it's a really strong star formation galaxy. Yeah, we don't have actually a conclusion slide. That's all. Thank you.
Thank you. Questions? Oops. Oops, pardon.
I have a question about extreme O3 galaxies. Do they reach theoretical limit of excitation for O3 per H beta ratio?
Can you repeat the question again?
Do O3 emitters reach the limit of theoretical O3 per H beta ratio?
I mean, their ratio is consistent, for example, with the local higher Z analogs. So it's not like, I mean, it's not like the most.
Yeah. But when you see on BPT diagram, there is a upper limit which O3 per H beta ratio can reach, and there is
Okay.
on the right hand you also have S2 per H alpha ratio when we consider that it's already not photoionized, but shock ionized. So I'm wondering if we can say something about these systems, for example, to say that it's already not case B ionization, but something else because they above this limit.
Okay, I didn't consider the BPT diagram, but rather the mass excitation diagram. Anyway, the demarcation line in the mass excitation diagram is similar to those obtained in the BPT. And if you remember the plot I showed, our galaxies lie like very close to the demarcation line. So yeah, very close to the limit for starburst galaxies.
Okay, I see. Thank you.
I don't know for the shocks, but we can talk about later.
Do you consider radiation from binary stars in Beagle?
I don't think that, oh, wait, no, Beagle does not use.
And do you think it may explain why you have more ionization?
Yeah, so binary stars would contribute to that, yeah.
Even at these ages? Even at these ages, you think it will play a role? Okay, good. Okay, so thank you.